is there anything deeper to the geometry of the cubic equation? Let's take one of this form right here, where the slope at the point of inflection is negative, and also its reflection. So you know with these, that there's exactly one maximum and one minimum. And then there's the point of inflection right at the center. We also know this is odd, so it has half-turn symmetry. But is there something deeper? Maybe some geometric fact that relates the roots of the cubic equation. Let's say the vertical shift is just right and it has 3 real solutions. Well, there actually is a property that we can use. We're going to try and use this to solve this kind of cubic equation, a geometric fact, a geometric property. So we're going to have a cubic just like above. It has to have 3 real solutions. Okay. And I'm going to highlight each of the roots, also the extrema, and then the inflection point right here. So what we can do, is place an equilateral triangle centered at the inflection point. It's going to be an equilateral triangle above the cubic, and then there's always going to be a way to rotate and scale this triangle. There's always going to be a way to rotate and scale this triangle such that all of its vertices are going to line up with the roots. So essentially we have like this, it's equilateral, and another thing is that if we draw a circle in the middle, circle like this, inscribed circle, what we're going to see is that the extrema are going to line up with its leftmost and rightmost points. Not necessarily what intersects the triangle, just its left and rightmost points. So these things line up here, this lines up here, this lines up here. Again, this is kind of approximate here, since I'm just drawing it out. Point of inflection, this lines up here, and then this lines up here. So this is very interesting and seems very promising. Probably like we're going to see some trigonometry or something like that. So let's try and find a way to solve this kind of cubic using this specific fact. So what can we start with? Well, let's just let the center to be HK, okay? This is going to be our coordinates. So HK be the center of the triangle, okay? And then with this circle, essentially when you have an equilateral triangle and an inscribed circle in the middle, that radius is called the in radius. So this is probably going to be useful. So we're going to let R be the in radius, and then, well, just thinking about it from here, again, the triangle could be rotated, and so it's not always going to be directly horizontal. So there's not that much of an easy way to just use straight up trigonometry with entirely the triangle in mind, try to travel along the sides or something like that. So what we think would be useful, I think what would be useful is an outer circle like this. And so the radius of this, because it's an equilateral triangle, it's going to be 2 times the in radius, okay? And this outer radius of an outer circle is going to be called the circumradius. So we're going to let 2r be the circumradius. Alright, so now that we have this, let's see, how can we find the vertices? Okay, so because when we got this outer circle, what I was thinking is if we find a way to travel around it, essentially using trigonometry, using a reference angle here, using some direction, right? Because you can't just travel directly horizontal, it has to be in reference to an angle. That's how you get this specific direction. Because again, the triangle could be rotated some way. So, with this, what we're going to have here, I'm just going to make it straight again. So, we're going to want to travel here, here, and here essentially. So, let's think about this. From the unit circle definition and polar coordinates essentially of any horizontal component here for some coordinate pxy. So again, this is the unit circle. We know that the horizontal component is going to be cosine of theta, and the vertical component is going to be sine of theta. It's here, and the radius is 1. And so what we can essentially do is scale it by any radius here. This one, it just got divided by 1, so it's going to be simply just 1. But in general, this goes to r sine theta and r cos theta. And so in our case, r, or the radius, is 2r from the outer circle, the circumradius. We have 2r. So the way that we can travel in a specific direction given this reference angle theta, so we're going to have 2r sine theta and 2r cos theta for specifically the vertical and horizontal components. But what we really care about is the vertical component, because we're not looking for the function at that point. It's going to be 0, we know that. I guess that's the way to check. But to find the roots, we're going to need the horizontal component, 2r cos theta. So what this is basically doing, you just have triangles over here like this, and we're traveling this way. So like, say this is the unit circle definition. This is just straight up cos theta, and then we're scaling it by 2r because that's what our circumradius is. And then look at it from here for the next one, and then one more time right here. And then, so that's how we're going to basically travel to get to the roots. So we have this angle here, theta, and it seems to be incremented by some amount each time, and eventually we're going to cover all of 2 pi radians. That's the entire coverage of a circle. So if we start at 0, so we're going to have theta, and then we basically have to we have to increment 1/3 of the circle each time. So that's going to be theta plus 2 pi over 3, and then one more time theta plus 2 times 2 pi over 3, which is 4 pi over 3. And then again, if you do it one more time, you're going to get 6 pi over 3, which is just 2 pi. So we basically circle back to the beginning. So that's how we can travel around to get to every vertice. Okay, and now let's not forget about our center. Our center, so what we have is x of n is equal to, so our center, its x-coordinate is h, that's the inflection point essentially, h plus 2r cosine theta plus 2 pi n over 3, and this is for n is equal to 0, 1, and 2. So this is basically our general formula for finding the roots of such a cubic equation. If we want to look at them numerically, instead of x1, x2, x3, just for the case of keeping n in the formula singly by itself, what we're going to have is, so x0 or x0, that's going to be h plus 2r cos theta. Then we're going to have x1, it's going to be h plus 2r cosine of theta plus 2 pi over 3. And finally, x2 is equal to h plus 2r cosine theta plus 4 pi over 3. And that is it. That is how we get all our solutions. So this is great and all, but how do we find all these values, h, r, and theta? That's what they basically depend on. Well, let's see what we get when we basically plug it into each of its factors and then try to expand. So we're going to have x minus x0, then x minus x1, and x minus x2 equals 0. And so again, this deals with so everything is a sum here, and then there's cosine of the sum of two angles. So this is going to get very messy, but I'm just going to tell you what you get to after you expand it. So eventually what we're going to get to is x cubed minus 3hx squared plus 3h squared minus r squared times x minus h cubed plus 3hr squared minus 2r cubed cosine of 3 theta equals 0. Now, okay, this is quite a thick equation here. So normally here we would compare coefficients and then try and solve from there. And you can essentially go one by one here, because that's h by itself, then you can get r by itself, and then you solve for theta at the end. But this is hard to remember. Well, the real main problem that we don't like here is this h over here. First of all, that can be trivially found just by, it's the inflection point, negative b over 3a. What if there was a way to get rid of this x squared term, and everything here would simplify? So what we can do is substitute x is equal to y minus b over 3a. What we're essentially doing is undoing the shift from the inflection point. So now the graph is going to be centered on the y-axis, and what's actually controlled is the x squared term. The x squared term controls this. So when you do this, is going to get rid of it, and what we're going to have, which is simpler, is y cubed minus 3r squared y minus 2r cubed cosine of 3 theta is equal to 0. So this is much nicer, and this one can be easily memorized, right? So this is what I'm mainly going to use, and again, at the end, all you have to do is just add negative b over 3a again at the end, right? That is, if it's not already in this simplified form. So let's try an example here. Let's say we have x cubed minus 12x plus 8 is equal to 0. So what we can do here is just align each term and their coefficients to each term of the simplified form, and then we can just solve from there for the variables. There's 2r cubed cosine of 3 theta. Okay, so now this aligns here, this aligns here, and then this aligns here. So what we get is the system of equations. So we have minus 3r squared is equal to negative 12, and then minus 2r cubed cosine of 3 theta is equal to 8. So that's what we have here. And so I'm just going to call this equation 1 and equation 2. So now we're going to solve equation 1 first. Okay. So what we're going to have is negative 3r squared is equal to negative 12. Divide both sides by negative 3, and we're going to get r squared is equal to 4. Okay. Now keep in mind the geometric intuition from this. Okay. We don't need to consider plus or minus roots here. All we're going to have is the positive one, because the radius here, this is essentially like a physical quantity. It's only going to be positive. Okay. Right? So r is greater than 0, right? So that means that all it's going to be is the square root of 4, positive only. So that means the radius is going to be 2. Okay. So that's what we have for r. Now we're going to solve equation 2. So we have minus 2r cubed cosine of 3 theta is equal to 8. So r is going to be 2. When we sub this in, we're going to get negative 16 cosine of 3 theta is equal to 8. And then we can just divide by negative 16, and we're going to get cosine of 3 theta is equal to negative 1 over 2. And same thing here. We don't need to find the angle in any other quadrants except for the first one, because the way we travel around to get to each of the vertices is just by an increment of 2 pi over 3. We don't need to find any of the other solutions here. So all we're going to get is 3 theta is equal to 2 pi over 3, the first one. And then we have theta is equal to 2 pi over 9. Okay, that's all we need. Right. Okay. So now we can just plug this in to our solutions here. So we're going to have x0 be equal to, so 2r, r is 2, so we're going to have 4 cosine of 2 pi over 9, and this is approximately 3.064. Then we have x1 is equal to 4 cosine of 2 pi over 9 plus 2 pi over 3, which is going to be approximately negative 3.759. And then we have our x2, which is going to be 4 cosine of 2 pi over 9 plus 4 pi over 3. And again, it's going to be approximately 0.695. So those are our solutions, and you can check it yourself numerically or through graphing software like Desmos. These are the solutions exactly. So how did this geometric fact come to be? Well, I'm going to give you some intuition about it relating to the standard cubic formula. So over there, for the case of 3 real solutions, the discriminant, which is inside the nested roots, that's going to be negative. So you're going to have to deal with complex numbers. Basically, you have the cube root of n plus negative m. Again, this is just arbitrary right now. And then plus the cube root of n minus root negative m. Okay. And so the negative m, that's the discriminant here. So you're going to have to deal with complex numbers. And so when you get to it here, on the complex plane, you're essentially going to have two conjugates here that you're going to have to add. And then essentially, so when you add conjugates, the imaginary parts are going to cancel out, and that's why we get 3 real solutions. So it's something like that, right? Now think about what the triangle does. You always have to rotate it and scale it by some amount to land on the roots. But isn't that the same as the behavior of complex numbers geometrically? Especially considering their polar form. They have the magnitude and then their phase. So that's essentially what it does. They're scaled and rotated. The rotation comes from the imaginary component. So this geometric fact actually still has heavy ties to the original evaluation from the standard cubic formula, Cardano's method. If you want to go even deeper as to where the triangle shape comes from, and you know some complex analysis, essentially the cubic is a conformal map, and you can solve it. You can solve this kind of cubic by getting the inverse of that conformal map. And you'll see from the W plane that the geometry, a equilateral triangle arises. And also from this, another byproduct is Marden's theorem, which here deals with a cubic with complex coefficients, and you get a triangle in the complex plane with each of its roots. So you have 1 point here, 1 point here, and 1 point here. And Marden's theorem, it states that if you have an inscribed ellipse right through here, if you have an inscribed ellipse, the foci of the ellipse will be the exact same coordinates as the extrema, or basically the zeros of the derivative of that cubic. So wasn't this so cool and interesting? Something as difficult to solve as a cubic equation has such an elegant and nice geometric solution. I hope you enjoyed this video, and I encourage you to stay curious, and I'll see you in the next one.